Welcome back. In the previous episode, we configured the AVR-ARM system clock to run at 84 MHz using pure register level programming. Now that the clock is stable and running at full speed, it's finally time to use it. In this episode, we'll do two very important things. First, we'll build our own delay function. No timers, no interrupts, and no libraries. Then, we'll use that delay to blink the onboard LED fully bare metal. Let's jump straight into the code. Here, we begin with defining our delay function. Static void delay _ms, and it takes UN32 _t ms. This function takes a single parameter, the number of milliseconds we want to delay. Inside the function, we define two loop counters. Volatile UN32 _t I, j. We mark them volatile so the compiler doesn't optimize the loops out. Without volatile, the compiler sees that we're just burning cycles with no side effects and could completely delete the loops, which would kill our delay. Now, we calculate how many loop iterations we need for roughly 1 millisecond. Const UN32 _t loop _per _ms equals f _cpu divided by 18,200 U. f _cpu represents the system clock frequency, in our case 84 MHz. By dividing it by a constant, we approximate how many iterations are needed to consume 1 millisecond of CPU time. This value is not mathematically perfect, and that's okay. This delay function is not meant to be precise. It's meant to be simple, predictable, and fully bare metal. Later in the series, we'll build accurate delays using hardware timers. And now, the heart of the delay, the two nested loops. For I = 0, I < ms, ++i. And for j = 0, j < loop _per _ms ++j. Double underscore ASM double underscore and double underscore volatile double underscore inside parenthesis NOP. The outer loop runs once for each millisecond, and the inner loop burns CPU cycles to create the time delay. Inside the inner loop, we execute a single NOP instruction, which means no operation. It tells the CPU to do nothing for one instruction cycle. By repeating this instruction many times, we intentionally waste time in a controlled way. Alright, delay function is done. Now let's jump into the main function. Int main, and it takes void. Execution starts here after reset. The first thing we do is configure the system clock. And here we say board _clock _2 _84 MHz. This ensures that everything that follows, delays, GPIO timing, instruction speed, is based on a known and stable 84 MHz clock. Next, we enable the peripheral clock for PIOB. PMC _PCER0 equals 1U shifted by ID _PIOB. If the peripheral clock is not enabled, the GPIO hardware won't respond. Next, we configure the LED pin itself, PB27, PIOB _PER equals LED _mask, and PIOB _OER equals LED _mask. PER says this pin is controlled by PIO, and OER says is an output pin, so we can drive it high or low. And finally, the infinite loop that keeps everything running forever. Well, 1. First action inside the loop, turn the LED on. PIOB underscore SODR equals LED underscore mask. And now we wait half a second so the LED stays visible. Delay underscore MS 500. Then we turn the LED off and wait another half second before the next cycle. PIOB underscore CODR equals LED underscore mask and delay underscore MS, and we pass in 500. And just like that, we have a fully bare metal LED blink running at 84 MHz with no interrupts, no timers, and no libraries. In the next episode, we're going to take a very important step and start working on the startup.c file. We'll look at what happens before main runs, how the stack is set up, how memory is initialized, and how the CPU actually jumps into our C code. This is where embedded systems truly begin, right at reset. If this video helped you understand what's really happening under the hood, make sure to like the video, subscribe, and leave your questions in the comments. Thanks for watching, and I'll see you in the next episode.